Swayam Prabha. Digital India. Educated India.
You see, towards the end of the last lecture, we were trying to understand the implicit function theorem. Okay, and this implicit function theorem is it's a pretty technical theorem in topology or analysis for that matter. And the only case where it is more or less easily deducible is the one-dimensional case, where it's more or less trivial or let me say easy to deduce. But if you go even to 2 dimensions, the function is not easy to deduce. Okay, I mean the implicit function theorem is not easy to deduce. So but what is the relevance of the implicit function theorem to whatever we are doing? It is relevant to the fact that when you represent a curve as by an implicit function, namely as a level curve of a function of 2 variables, then you want to say that that is also parameterizable in a nice way. You want to say that that is also really a curve. Okay, I mean, first of all, you need the guarantee that if you take a function of 2 variables and look at the loci where the function takes a constant, the locus where the function takes a constant value, what is the guarantee that it is a curve? Okay, so the idea is that you are in 2-dimensional space and you are having a function in 2-dimensional space. In the 2-dimensional space, there are 2 variables, x and y. They are independent variables. Okay, the dimension is the number of independent parameters, so there are 2 variables. So it's 2-dimensional space. In that, you are writing one equation, f of x comma y equal to constant. Okay, and every equation you write heuristically reduces the dimension by 1. So the effective dimension is 2 independent variables. So 2 dimensions minus 1 equation. So you get 1, and therefore the locus is 1-dimensional, so it's a curve. Okay, this is the heuristic way of saying it. But you need to really prove all this. And in fact, what you have to show is that if you want to really see it as a curve, then in the most basic sense, you should see this as graph of a real valued function of a real variable. That you can do it at every point. That's exactly what the implicit function theorem says, provided your locus is smooth. Okay, and the smoothness is now interpreted as the gradient never vanishing. Okay, so let me explain with one example, one very simple example, which is the the circle case. Okay, so watch carefully. See here, so this is R2. Okay, and these are the x and the y. These are the x and the y coordinates, and then the x and the y axis, and the coordinate axis, and then you have this function f of x comma y is equal to x squared plus y squared. Okay, mind you, this is a function that is going into the real line. Okay, and in principle, I could have taken fxy to be also square root of x squared plus y squared, which is actually the distance of the point xy from the origin, if you want. Okay, but let me take it like this. Okay, so if you take a constant c and assume that c is greater than 0, and you look at the locus where f is equal to c, this is simply the points which satisfy x squared plus y squared equal to c. Okay, and this is a circle which is a circle with radius positive square root of c centered at the origin. Okay, so the level curves are just circles. All right, and here of course I am taking c equal to 1. If you take c equal to 1, you get the unit circle. Okay, now just look at what is happening with the unit circle. So this is a typical case. This is a typical case, and what happens in this case happens in general. Okay, and so if you understand this case, you understand the statement of the theorem. Of course, it is another matter to prove the theorem itself. All right, so so look at this carefully. See, the function is so the point is that recall what is the smoothness idea? The smoothness idea geometrically is that at every point you should have a tangent line, all right, and that is the same as saying that at every point you have a normal line, okay, and because the existence of the tangent is the same as the existence of the normal, okay, it's tautological. Now the point is that the normal line direction is given by the ratios are given by the gradient components. So what happens is that, you know, if I take a point here, all right, then what happens is that the normal direction, so you have the, so if P is a point here, then this is the tangent direction, TP is the tangent line, and let me not put an arrow because I am only interested in the line. So this is the normal, this is NP is the normal line, okay, this is 90 degrees, okay, and the point is that this direction or the slope of the normal, that is, you know, that is controlled by the components of the gradient. So this normal direction is given by, you know, fx comma fy, okay, and where of course fx is dou f by dou x and fy will be dou f by dou y, and if you in this particular case, you know, f is x square, f is x squared plus y squared, so fx will be 2x and fy will be 2y. So what you will get is basically you will get 2x comma 2y. This is what you will get. Okay, that is a normal direction. All right, and what I mean by saying that is a normal direction is that, you know, these you know, these give you the, you know, this will give you the slope of the normal if you want. All right. Now the ratio will give you the slope of the normal if you take the right order. All right. Now you see, now look at what is happening. Look at what is happening for this gradient. So this is the gradient of f. Okay. Look at what is happening for the gradient. Can the you see can the gradient ever vanish? So mind you, for the gradient to vanish, 2x 2y must be 0 0. That means xy must be 0 0. But that cannot be possible because 0 0 is the center and you are looking at a point on the circumference. Therefore you see that this is never 0. It's never 0. Therefore what I mean is never 0 comma 0. Okay. So that this tells you that there is a well defined normal at every point. All right, and that in turn tautologically is the same as saying that at every point there is a tangent. So the circle is a smooth curve. Okay. Not only that, how are the directions given by? They are given by this ratio 2x 2y. Okay. And mind you, 2x and 2y are also continuous. This 2x comma 2y is also continuous in the point x comma y. Therefore you also see that these normals are continuously varying. Therefore the tautologically any statement for the normals is also the same as the statement for the tangent. So it means that every point, not only do you have a tangent, the tangents are also continuously varying. So it is C1. Okay, so it's first continuously differentiable. Okay, it's a smooth curve. Okay, but there's still something that you have to understand. We want to look at it in the simplest form, namely that. So when I say, so let me make that statement also here. F is C1. Okay. F is C1. So mind you, now F is a function of two variables. Saying what is C1? It means first continuously differentiable. What does that mean? It means all first derivatives exist and are continuous. Now this is a function of two variables, so the derivatives are partial derivatives. So it's fx and fy, and what you want is fx and fy should exist and they should be continuous. Okay, and mind you, f is this fx and fy being continuous. Mind you, f is a function of x and y, so fx and fy are also functions of x and y in general. And what you are requiring is these functions of x and y should be continuous as functions of the point x comma y put together. Okay, so it's a, you know that continuity in two variables is not the same as continuity in each partial variable separately. Okay, so this is a very strong condition when you say that, you know, a function of two variables is continuous. Okay, even though you may have an expression which might tell you that partially in each variable it is continuous. There is no guarantee that jointly it's continuous in both the variables as a point put together. Okay, you have to be careful about that. So it's a very strong condition. F is actually C1. Okay, now look at what happens. Let's look at 4 points. So let me look at this point. Okay, so let me first look at this point, let us say. All right, if you look at this point, so this point is x equal to 0, y equal to 1. Okay, if you write the gradient here, the gradient will be, so I have to just substitute in this 2x comma 2y. Okay, so this is going to be 0 comma 2. All right, and here what happens is that, of course, what is happening here is that you see fx is 0. Okay, because fx is 2x, x coordinate is 0, and fy is not 0. Okay, see, this is what is happening here. And you see, look at what is happening. I can write in a vicinity of this point. Okay, in the vicinity of this point. Okay, so let me draw it like this. I can write out this curve as the graph of a function. Actually, I can write this as, you know, graph of y is equal to, you know, a positive square root of 1 minus x squared. Okay, I can write it like this. Okay, and what I want you to understand is that where is this valid? This is valid all the way at every point on the circle. Okay, it is the upper for the whole upper semicircle. This is valid. Okay, so it's not valid at these 2 points on the x-axis. Okay, because there, you know, if you go below that, you will have to take the negative square root. Okay, so what happens is that if I so similarly, let me write out at this point. If you go to this point here, okay, here this is 0 comma minus 1. Again, the gradient is going to be, by the way, why do we consider the gradient? We are using this result from multivariable calculus, that the gradient of a function is normal to the level curves of the function. The gradient gives the direction of maximum change of the function, and it's orthogonal to the direction where the function doesn't change, which are the level curves. Okay, we are using this fact from calculus. Okay, so the gradient at this point 0 comma minus 1 is what? Is going to be, I have to substitute 2x 2y, I'll get 0 comma minus 2. Okay, and that is of course not 0. So you see the gradient is not 0 here. Of course, it's not 0 throughout. But the point is, look at what fx is. Fx here is again 0, and fy is not equal to 0. Fy is minus 2. Okay, and watch again. If you take this portion of the curve, okay, this is writable as graph of a function of a real variable. So you can actually write this as graph of, you know, y is equal to negative square root of 1 minus x squared. Okay, I can write it. And where is this valid? This is this whole lower branch of this circle, namely the lower semicircle. It's valid. Okay, so so the issue is only at these points on the x-axis. Okay, now look at what's happening at the point on the x-axis. Make a similar analysis. Okay, so what happens at the point on the x-axis? So let's look at this point here. This point is 1 comma 0. Okay, then the gradient at this point is going to be, I have to substitute 1 comma 0 in this. Okay, so I will get 2 comma 0, and of course the gradient is not 0. Okay, and here what happens is fx is not 0, but fy is 0. Okay, fx is not 0 and fy is 0 because fx is actually 2 and fy is 0. Okay, so now watch. Look at a small portion of the curve at this point. Is this still the graph of a function of a real variable? Yes. Okay, because I can still write it as x equal to positive square root of 1 minus y squared. It is still the graph. So, you know, here again it is graph of x is equal to positive square root of 1 minus y squared. I can write it like this. Okay, I can still write it as the graph of a function of one real variable. And where is this valid? Mind you, this is valid, on the right semicircle, except for the points on the y-axis. So it's valid from, see, I put a blue circle here to say it's not valid there, but it's valid throughout. Okay, all right. And now if you repeat the same argument, you will see that, if I come to the left semicircle, okay, again what will happen is that at this point, for example, this is minus 1 comma 0, the gradient is going to be minus 2 comma 0, which is of course not 0, and then fx is minus 2, which is not 0, and but fy is 0. Okay, now I want you to notice the following thing: at all the points the gradient is not vanishing. Okay, at the point where you see fy is not 0, take the point on the positive y-axis. Where fy is not 0, I am able to write the curve as graph of y is equal to root of 1 minus x squared. Okay, and look at the point in the negative real axis, on the negative y-axis. There also fy is not 0, and I am able to write y as a function of x. Okay, so watch, if fy is not 0, I am able to write y as a function of x, and the curve there is graph of that function. Okay, look at what's happening here. Here fx is not 0, okay, and I am able to write the curve locally as graph of x as a function of y. So when fx is not 0, I can write x as a function of y. And what is happening here, you see again, fx is not 0, I can still write x as a function of y, namely x is negative square root of 1 minus y square. Okay, so you see what is happening. The gradient never vanishes. At a point where fx is not 0, I can write x as a function of y, and the curve is actually graph of that function. At a point where fy doesn't vanish, I can write y as a function of x, and the curve is the graph of that function. So at every point, since the gradient doesn't vanish, it means that fx, fy don't simultaneously vanish. So at least either fx doesn't vanish or fy doesn't vanish. Therefore, at every point, either you should be able to write the portion of the curve as either graph of either as x as a function of y or y as a function of x, and graph of that function. Okay, so you see, therefore this is the implicit function theorem. All right, so let me write it out. So if you understand this example, you understand the theorem. Okay, proving that is of course involves some topology and some analysis. Okay, and it involves work, but at least up to this point, understanding the statement of the theorem is very clear, and why it's helpful to us is because whenever we are going to represent a curve by an implicit equation, like for example the circle x squared plus y squared equal to 1, you can be guaranteed that you can always write it as graph of a function of one real variable, and graph of a function of one real variable you can always parameterize it nicely. Okay, because you can take that variable as a parameter. Okay, for example, what is the parameterization for this? So look at the upper semicircle. What happens is that fy is not 0, so you are able to write y as a function of x. So this upper semicircle can be parameterized by taking x as the independent variable. So you can write the parameterization t comma root of 1 minus t square. This is the parameterization. Okay. So and similarly, if you take this part, you can write the parameterization will be t comma minus root of 1 minus t square. That will be the parameterization. Okay. And similarly, if you take here, you can take, so you see x is the dependent variable. Okay, y is the independent variable now because x is a function of y. So y is the independent variable. Take the independent variable as a parameter. So this parameterization will be root of 1 minus t squared comma t. If you put y equal to t, x will be root of 1 minus t squared. Okay, and here what is going to happen? Here the parameterization will be again x is a function of y is independent variable, x is a dependent variable. So take the independent variable always as a parameter. So you will get t, and then it will be minus root of 1 minus t squared comma t. That is a parameterization. Okay. So the moral of the story is that you see you are getting a parameterization, nice parameterization at every point. So this also tells you that parameterizations are there, but they come from this implicit function theorem. Okay, you have to understand that. So let me again repeat, I am going to write out the conclusion of the implicit function theorem. So if fy is not 0, then y can be written as a function of x. Okay, and you see if fy is not 0, the other variable is x. Okay, that variable can be taken as independent variable, and you can write y as a function of x, and the curve is locally graph of that. Okay, so that's exactly the statement. So if f is C2 in an open set in R2 or which can be the whole of R2, and the gradient of f never vanishes. Let me say even at a point, gradient of f does not vanish at x0 comma y0. Okay, then there are two cases. Okay, mind you, the gradient of f is just fx comma fy. Okay, I am writing it as components, but you are probably you also write it as a vector, I dou f by dou x plus j dou f by dou y, where I and j are the unit vectors along the x and y directions. But we will always use this duality that a point coordinates of the point are also components of the vector, position vector of that point with respect to the origin. Okay, so this is the gradient, and you see the gradient at x0 comma y0 is not 0. Okay, that means this is fx at x0 comma y0 comma fy at x0 comma y0. This is not 0. All right. Now, when an ordered pair is not 0, there are two possible cases. Each entry being non-zero is a case. So, case 1, you can have fx of x0 comma y0 is not 0. Okay, the partial derivative of f. So then what happens? All right. So in fact, I think I have put C2. I don't have to put C2. Let me put C1. Okay. So I put C2 because I was interested in curvature. Okay, and because curvature will involve the second derivative. So I impulsively put C2, but C1 is enough for the implicit function theorem. But when we do the curvature calculations, we need second derivative being continuous. Okay, so that will come on later. But for the implicit function theorem, you don't need C2. First continuously differentiable is enough, which is the same as saying fx and fy exist and are continuous. And let me say with a word of caution, continuous means fx and fy are continuous as a function of two variables. Okay, that is somewhat serious. Okay, so if what happens if fx is not 0? So this is this case. Look at what's happening at 1 comma 0. At 1 comma 0, you see fx is not 0, and look at what is happening. You are able to write x as a function of y. Okay, so and the portion of the curve, the locus, is actually graph of that function. Okay, so let me write this. Then we can see the locus near x0 comma y0 as graph of x is equal to g of y. You can write. So you see, let me repeat it again. If fx is not 0, you are able to write x as a function of y. That means x becomes a dependent variable, y is independent variable, y is the other variable. Okay, so basically what is happening is that fx is not 0, then x becomes a dependent variable and y becomes an independent variable. So x is a function of y, so that I am writing as x equal to gy, and its graph is exactly the locus there locally. Okay, and you have a similar statement for the other case. If fy is not 0, then what happens? So which that's my diagram here. So I will just continue it here. Let me write it here. If so, case 2 is case 2 is fy of x naught comma y naught is not 0. Okay, if fy is not 0, then we are in this kind of situation. So you see, fy is not 0, then you are able to write y as a function of x. Okay, and the curve is locally at that point the graph of that function. So I'll just write it here. Then the locus is so the of course, what is the locus? Is the locus given by f equal to constant. Okay, the level curves. Okay, then the locus is nearby near x naught comma y naught. The graph of y is equal to fx. Okay, so that is the second case. Okay, and that's exactly what is happening here, right? And not only that, so let me make one more statement. There are situations where both case 1 and case 2 will simultaneously hold. Okay, so if you leave out the 4 points on the axis, okay, 0 1 0 minus 1 1 0 minus 1 0, at all other points you see both fx and fy are both non-zero. So you can write both, x as a function of y and y as a function of x. So for example, if you take the quarter circle in the first quadrant, there you can of course write x is positive square root of 1 minus y squared. You can also write y is positive square root of 1 minus x squared. So it's both cases will work. Okay, so I'm not saying that case 1 and case 2 are exclusive. Okay, they can both hold at a point. But what is important is that the locus is graph of a function of one variable locally. Okay. Globally it is not. You cannot globally write it as graph of a function of a single variable. Okay, for topological reasons. Okay, you cannot do that. But locally you can always write it. And that is what we need. We need the assurance that such a locus is always a curve. Okay, and that it can be given a nice parameterization. All right, and the parameterization will be regular. Why? Because you see, for the parameterization, if you look at it, I have already told you, when you take the parameterization for a curve which is given by graph of a function of one variable, then automatically that parameterization is regular. Okay, because that one of the two functions will be that variable itself. So if you differentiate with respect to that variable, one of the derivatives will be 1, so it will never vanish. Okay, so in this case, for example, you see here it is t 1 minus t squared. T is a parameter. If you calculate the tangent vector, the tangent vector will, I have to do d by dt. So this t will return 1. All right, and so I will get 1 comma something, 1 comma derivative of root of 1 minus t squared with respect to t, and that's never going to vanish. So I have this condition that I have a regular parameterization, namely parameterization for which the tangent vector never, the velocity vector never vanishes, and that is a very important condition for that is the analytic condition for regularity. Okay, so what we have proved is that if the gradient never vanishes throughout, then analytically it is regular and geometrically also regular. Okay, and so everything is nice. Okay, and we can go ahead with our theory. Okay, and in fact I want to say that with this background, what we are going to do is from now on, what we will do is that whenever we say curve, we will always assume that the curve is regular. Okay, and whenever you want to work with it, you always take only a regular parameterization. Okay, and mind you, the motivation for all this is the regularity condition is that the velocity vector never vanishes. That was needed in our geometric derivation for curvature. All right, so you have to understand that. Okay, so let me write this down here. So from now on, we shall always assume that we are working with a regular curve, okay, which is of course regular means that which is given by a regular parameterization gamma of t in AB with mind you, we want to talk about curvature, so it should be second continuously differentiable. So with gamma belonging to C to AB, okay, that is in other words, gamma dot, which is d gamma by dt, and gamma double dot, which is d squared gamma by dt squared, are all continuous on AB. Okay, so this is the assumption we will make. Okay, and it will so this will be always at the back, when we do further, when we proceed further. All right. So what has happened is, all this you see, all this effort is just to tell you that when you are trying to compute the curvature of a curve, you make sure that you use a parameterization for which the velocity vector does not vanish. Okay, that's all. That is regularity, and it can be thought of as analytic regularity or geometric regularity. Analytic regularity means there is a parameterization like that. Geometric regularity is that basically the curve has a continuously varying tangent at each point. All right. Okay. Now we are still we still have the following problem. The problem is how do you define curvature? Still we have not defined curvature for an arbitrary regular curve. All right. So here is where we will use a little bit of there's still one step that needs to be done, and that is I would say called the normalization of speed. Okay. So this is something that has to be done. Okay, and I am coming to that concept next. So to motivate that concept, what we will do is we look at something connected with physics and physical perception. Okay, so what we are moving towards now is trying to define curvature. So the status is, okay, suppose I am giving you a curve which is regularly parameterized. So it's given by a gamma t, where t is varying on an interval in the real line, and this gamma is second continuously differentiable, and gamma dot never vanishes. Okay, the velocity vector never vanishes. That's regularity. Okay, now how are you going to define the curvature at a point? All right. Now this definition of curvature that I am going to give is an analytic definition, as against the earlier definition that we started with, namely you tried to show that there exists a best approximating circle, call that best approximating circle as circle of curvature, and take its center, find the center of curvature and show that center of curvature exists, and then you get the radius of curvature, and the curvature is just the reciprocal of the radius of curvature. So that was a completely geometric argument. Now we have to do it analytically, so that you get an analytic formula. Okay, so if you recall, for gamma t, if gamma is given by if gamma is given by x comma y, I am suppressing t, so actually I should have written gamma t is xt yt. You recall that if it is like this, then the curvature is given by x dot y double dot minus y dot x double dot mod norm of this, modulus of this, divided by square root of x dot squared plus y dot squared to the whole cube. Okay, this is what it is. And if you write it in terms of gamma, this is just gamma dot cross gamma double dot norm of this vector divided by norm gamma dot to the 3 by 2. Okay, so we derived this. Okay, and yeah, so I should be careful when I write as gamma dot. I should write as gamma dot to the power of 3. Yes. Okay, so watch out for that. Okay, so because gamma dot is this norm gamma dot is the speed is square root of x dot squared plus y dot squared. Okay, so it should be norm gamma dot cross gamma double dot by norm gamma dot cube. All right, and see, you want to get this formula in general, and I want to get this formula not using geometry, here's the point. I want to get this formula, which I originally got using geometry. I want to not use geometry. I want to use pure calculus and get this formula. Okay. So that means that I have to give you an analytic definition of curvature. Okay. The way I got this formula was I used a geometric definition of curvature. Basically what I did was I said find the best approximating circle, right? How did I find the best approximating circle? Geometrically I did the following thing. I took for the curve at a given point, I took the normal, I took a nearby point, took a nearby normal, these two normals hit at one point. Now I show that as this nearby point approaches a point on the curve, this point of intersection, that approaches a finite limit. Both coordinates approach a finite limit, that point I call it as the center of curvature, and then I get the radius of curvature and so on. Okay, so it was completely geometric, but now I want everything to be analytic. Okay, so you see, so this whole, you see what is happening. Originally we drew a picture of a curve, okay, and then we took a parameterization and then we made a computation, but we were using geometry. Okay, now what you are doing is you are making it completely analytic, no pictures. Your curve is now just regularly parameterized curve. That means I am just giving you a function gamma, which is from an open interval of r into r2. Gamma is second continuously differentiable. Gamma dot never vanishes. Now for that, without any geometry, define the curvature and get a formula like this. Okay. Of course, the fact is that some amount of geometry will be used, but we will not do that very extensively as we did earlier. All right. So I am just saying that this is all to define curvature. But then even before doing that, there is a requirement for normalization of speed, which is what I want you to understand. So what is that? So you see, just think about it. So so there are two aspects. The first thing is, what is the, so I will just write it as, the need for normalization of the speed. Okay. So this is what I want to talk about next. So we'll look at various inputs from physical perceptions and also from physics. So here is the first thing. So look at circular motion. So input from uniform circular motion. So you see, you take an object moving in a circular path, okay, and let us assume that the object is moving with speed. So here is I'll just put it like this. Let this be the radius of the circle, okay, and here is an object on the here this moving, all right, and this has, let us say, speed v. Okay. So you all know that there is to sustain this motion there is a centripetal acceleration, and that is given by v squared by r. Okay. So centripetal acceleration is equal to v squared over r. Okay. And this is something that you learn in basic physics. All right. And mind you, why you need this is that at any point the object is moving on the circle. At that instant, it is trying to move. You can think of it as moving tangent to the circle. So if no force were acting on it, it will just go along the tangent. It will never remain on the circular path. So in order for it to remain on the circular path, it needs to be continuously pulled into the center of the circle, and that's your centripetal force. All right. Now watch. You see this centripetal acceleration. You see, I told you the idea of curvature should be acceleration. Okay. Idea of curvature must be acceleration. All right. And why is it also mathematically correct? Because you see, what is acceleration? Acceleration is second rate of change of displacement. okay, or rate of change of velocity, okay. But you see the velocity is actually the tangent vector, and it's the rate at which the tangent is turning that should be the curvature, and the rate at which the tangent is turning is actually rate of change of the velocity vector, so it has to be the acceleration vector, okay. So if you believe that acceleration should be your curvature, look at this formula. What is this formula telling you? It's telling you that your curvature depends on v. If I suppose I fix the radius and I travel at different speeds, then my acceleration is changing. If v increases, my acceleration is going to increase by square of v, okay, it's proportional to v square. So this tells you that your perception of curvature is affected by the speed at which you travel, okay. So if I have circles of different radius and I want to perceive curvature, if I want to use the formula v squared by r, I had better use the same v everywhere, okay. If I used different v's, okay, then I am not going to get a honest, because a curvature of circle of radius r must be 1 by r, okay. And here to get 1 by r, you can see v has to be 1, okay. So if you take any circle, if you take uniform circular motion, okay, you will get the correct curvature, okay, as you expect, only if you take unit speed, okay. If you go in unit speed, then v is 1, then the acceleration is 1 by r, v squared by r will become 1 by r, and that is the curvature. And of course reciprocal of that is r, which is the radius of curvature, which is the radius of the circle, of course, all right. So this tells you that you have to measure if you want to really think of curvature as acceleration, you should keep the speed constant, and in this case actually you should take it as unit speed, okay. So let me say that here, if curvature, so I'll just write it. You see, curvature should be the rate of change turning of the tangent gamma dot, okay, and therefore this will be gamma double dot, and this should be acceleration, okay. But to get curvature of a circle of radius r to be 1 by r, we need to take v is equal to 1, that is unit speed, okay. So mind you, I am not saying unit velocity, that's not correct, because you see the speed is a scalar, that is constant. But if you take the velocity vector, that's not constant, because even though the magnitude is the same, the direction is continuously changing, all right. So you need unit speed. Now let us also look at an input from physical perception. Let me tell you something about physical perception. I am just looking at trying to define curvature as acceleration. What are the pitfalls? The simplest case is uniform circular motion, all right. See, let us look at physical perception. Imagine you are traveling on a, let's say, bike, okay, and you are going to negotiate a turn, all right. Look at what you will do. See, if the turn, the way you turn is you slow down and then you start turning, and then after your turn you continue, okay. So the point I want you to understand is that how much you slow down depends on how sharp the curve is. If there is if the curve is very mildly curved, what does that mean? It means the radius of curvature is large and the curvature is small, okay. In that case, you don't have to slow down much. So if it's just a small turn, I can just tilt a little bit and I can go, okay. I don't have to reduce my speed if you want, if I'm going at a decent speed. But suppose I have a sharp corner where I have to turn. You see, what I will do is that I will reduce my speed and then I will negotiate the turn and then continue, okay. So you see what is it that you are trying to do? You are reducing the speed in proportion to the curvature for you to comfortably, turn. Okay. For when the curvature is less, you don't have to reduce the speed much. But if the curvature is more, you have to reduce the speed a lot. Okay. And the net effect of this is that what this is supposed to mean, okay, is that your perception of curvature is controlled by your speed. It is affected by your speed. Okay. And of course, physically the reason why you need to slow down and turn, and why you need to slow down is because at the point where you are turning, okay, you need the road to be banked, okay, and there is the friction is going to give the necessary. There is a component of the friction or the reaction of the weight of the vehicle that is going to give you the centripetal force, and that so that you don't go off tangent and crash, you cannot exceed a certain speed. That is the reason why you have to go slower. Yes, this is what physics tells you. But what I want you to understand is just qualitatively, you see, the perception of speed is controlled by, it affects your perception of curvature. Okay, and the speed at which you negotiate a turn is controlled by how sharp the turn is. Okay, therefore so suppose you are supposed to you are asked to assess the curvature of, let us say, two circular racetracks of different radii. Okay, if I am in a circular track of smaller radius, okay, that means the curvature is large. Okay, then and I have to negotiate, I have to go around that. And suppose I have another circular track whose radius is large, that means the curvature is small. Okay, in both of them, you see, I will be able to get the if I move comfortably so that I don't feel any discomfort, then for the sharper track I will move slower. Okay, the smaller circle I will move slower, and for the larger circle I will move fast. I could move faster in principle. Okay, and when I do that, I am comfortable. So that means actually I have not sensed the difference in curvature of these two. If I want to sense it, what I should do is that on both I should move at the same speed. In the smaller track also I should move at, let us say, 20 kilometers per hour. In the larger track also you move at 20 kilometers per hour. Then you will see that in the smaller track it's more difficult to turn than in the larger track. And therefore you see this, the higher curvature here, you can feel it in the smaller track, the larger track. So therefore this is again a physical qualitative thing that's telling you that if you are moving along the curve, your speed influences how you analyze or how you perceive the curvature of the curve. Therefore, what this tells you is that if you want to make the perception of curvature independent of speed, you had better fix the same speed everywhere. Then your perception will be correct. Okay, and that means you have to have constant speed. All right, and therefore this also tells you from physical perceptions that if you want to measure curvature, okay, correctly without the speed affecting you, you should have speed as a constant, and that normally whenever something is a constant, we take it as 1. Okay, so you take unit speed. So all this motivation is to tell you that I am going to do the following thing. I am going to define the curvature as acceleration of a unit speed curve which is given by a regular parameterization. That is going to be the definition. Okay, that leads to the correct definition of curvature. And the beauty of that definition is, from that definition, without using any geometry or limiting process, directly using calculus, you can get this formula for curvature: kappa equal to norm of gamma dot cross gamma double dot by norm gamma dot cube. You will get that directly using vector calculus. Okay, so the upshot of all this is that you have to bring in unit speed. You have to bring in normalization of speed. Okay, okay, and so let me write this. when input from physical perceptions of curvature while turning to keep perception independent of speed, let the speed always be constant, and we take that constant speed as unit speed. Okay, so I will just write out the final definition. So we define a definition for a regular curve parameterized by gamma of t belonging to AB open interval in R. T is C2, I mean gamma is C2 of AB, gamma is second continuously differentiable, and gamma has unit speed. Okay, norm gamma, the curvature at the point corresponding to gamma t is kappa of t. So let me write the kappa of t is equal to norm of gamma double dot, which is the magnitude of acceleration. Okay, so the magnitude of the acceleration for a unit speed curve at every point is the curvature. That's going to be the definition. But then this will lead to one question. Here I am taking a regular curve. Because it's a regular curve, that means there is a regular parameterization. That only tells you that there is a parameterization with never zero velocity. That means at every point the velocity is not zero. Okay, but I am saying also make it unit speed. That means I am saying make the magnitude of the velocity 1. So I want a parameterization for which the magnitude of the velocity is 1, and for such a curve I define the curvature as the acceleration. Okay, this raises a question. Why should there be, for a curve with a regular parameterization, a parameterization which has unit speed? Okay, so again calculus comes to our rescue and tells you that don't worry, there is such a parameterization. And guess what is the hero of that parameterization? It's nothing but the arc length. Okay, you can measure the arc length of the curve, and looking at the arc length will ensure that every regular parameterization, that is a parameterization which has never vanishing velocity, can be made unit speed by a reparameterization. Okay, so that is the next thing that we are going to. And once we prove that, we can always follow this recipe. Start with a regular curve, take a regular parameterization. You can reparameterize this regular parameterization so that it becomes unit speed. Then simply compute the acceleration. That's your curvature, and that's the definition. Okay, so we'll come to this in the next lecture. All right, so I'll stop here.